In this section, we're going to talk about Riemann sums. The motivating factor for this section is that we saw geometry doesn't work really good without straight lines. In other words, if I'm looking for the signed area of a function, that is the area between the function and the x-axis, to try to get an exact area is doable when I can break my function into triangles and rectangles. But if I want an exact area and I'm dealing with a function like x squared is not going to have a graph with a straight line in it. So instead of getting an exact area using geometric principles, we are going to approximate the signed area, and we're going to use rectangles to do that. That's the big idea of Riemann sum. Geometry doesn't always give me an exact area, so instead, we're going to approximate the area under a curve with rectangles. Let's take a look at this example. We want to approximate the signed area of f of x equals 3x minus x squared on the closed interval from 0 to 3 using 6 rectangles. When we say using 6 rectangles, in this section, we mean a very specific thing. I'll discuss that as I draw the picture. But first, let's look at the signed area of 3x minus x squared on the closed interval from 0 to 3. I have graphed f of x equals 3x minus x squared. You can see 0 at the x value of 0, and at the x value of 3, we cross the x-axis. If you're looking for the signed area from 0 to 3, that means the area underneath this parabola. So the area that I have shaded in blue is the signed area. If I were to try to use geometry to get an exact answer, it'd be really tough because of the curvature of this curve. Because I don't have straight lines, or I don't have a geometrical figure that off the top of my head I know, it's very difficult to understand where and how to use some geometry formula here. So instead, what I'm going to do is I'm going to break this into 6 rectangles. Now, the rectangles we're going to use are going to be vertical rectangles. And there's a couple of options that we can do. I've just split my x-axis into intervals of 0.5. Now, the reason I'm going to do it this way is because I am going to create rectangles which have all of the same widths. So all of the same widths, meaning on the x-axis, they're going to be equal in width. So along the x-axis, equal in width. Think of like width and then heights. So my first rectangle is going to have width from 0 to 0.5. my next rectangle is going to have width from 0.5 to 1. My next rectangle is going to have width from 1 to 1.5, and so on and so forth. You'll notice if I do that, I get 6 vertical rectangles. Now, how far up do we want to go? That's the question. Well, we want to go up until we hit the curve. So maybe what I'll do is take this first rectangle and I'll use this point on the graph of 0.5, 1.25. If I do that, my rectangle is going to look like the following thing. So what I have done is I've created a rectangle whose height is the same as the function value at 0.5 and whose width goes from 0 to 0.5. Obviously, this rectangle is an overestimate of the area underneath the curve in that region. But it is an estimate. So it might not be a very good one right now, but it is an estimate. And then we go and do the same thing from 0.5 to 1. We're going to create a rectangle whose height is the same as the function value and whose width goes from 0.5 to 1. Let me type that in as well. And you can see that rectangle there. Okay, let's do another rectangle from 1 to 1.5. Again, the height of the rectangle is going to be whatever the function value is at 1.5. So the y of the rectangle is going to be the function value at 1.5, and the width of the rectangle goes from 1, again, x value of 1, to an x value of 1.5. We can do the same thing for the next rectangle. The next rectangle is going to have height of the function value when x is 2. So the height of it is going to go from 0 to whatever the output of the function is at f of 2. And the width goes from 1.5 up to 2. Notice that this red rectangle is an underestimate of the area under the curve in that region. That'll be the same for 2.5 and 3 as well, from the rectangle we create from 2 to 2.5 and the rectangle we create from 2.5 to 3. Both of those will be underestimates as well. Let's do those rectangles. The y value is going to go from 0 up to the function value at 2.5. The x value is going to go from 2 to 2.5. I get that rectangle. Now this final rectangle is going to be an interesting one. It's going to go from a y value of 0 up to a y value of what I get when I plug in 3 into the function. Notice when I plug in 3 into the function, I just end up with a 0. So in other words, this last rectangle has no height. And the width, though, is still from 2.5 to 3. You can't really see it, but it's a rectangle of height 0 here at the end. So what's happening is that these 6 rectangles, the 5 you see here and then the rectangle whose height is 0, all end up adding up to something that approximates the area under the curve. Now, again, some of these are overestimates, some of these are underestimates of the area under the curve, but it does give you an approximation. Let's go ahead and do this algebraically to see how this would work out algebraically. Remember, we want to approximate the area on the interval from 0 to 3. All right, we want to do that with 6 rectangles. So algebraically, what we could do is we could say the width of each rectangle, since we go from 0 to 3, and we want to divide into 6 rectangles, the length of the interval is 3. I want to divide that by 6 pieces. That means the width of each rectangle is going to be 1/2. We create 6 different rectangles. You could see how I did this. The area of each rectangle is just the width times the height, or the width times the length, whichever term you prefer. So we're going to get the area is equal to width of rectangle 1 times length of rectangle 1. In fact, I'm going to switch that up. I'm going to say length times width. Length of rectangle 1 times width of rectangle 1 plus length of rectangle 2 times width of rectangle 2 plus, we need to keep going over and over, length of rectangle 3, width of rectangle 3, length of rectangle 4, width of rectangle 4, plus length of rectangle 5 times the width of rectangle 5, plus the length of rectangle 6 times the width of rectangle 6. When you add up all those lengths times widths, you get the total area approximation for the signed area that we were dealing with. Now, what we just said is that the width of every single one of these 6 rectangles is going to be 1/2. That's going to be a common feature amongst everything in this section. In this section, when I say create 6 rectangles, we're going to force all 6 rectangles to have the same width. If I said create 10 rectangles, we'd force all 10 rectangles to have the same width. So we're going to force each rectangle to have the same width. In this calculation, in our scenario, that means each of these W's can get replaced with a 1/2. I'm going to write 0.5 instead of 1/2, but either way, if you'd rather write that as a fraction or a decimal, it's all the same. At this point, we need to figure out what the lengths are. Based on what I just did, I used the right-hand values to give me the height of the rectangles. In other words, in each one of these little intervals, I use the right-handmost value, the 0.5 for the first rectangle, 1 for the second rectangle. And in order to get the height of the rectangles, or the length, if you want to call it length, you have to plug in f of the right-hand part of our interval, our sub-interval. So essentially what I do is I take our interval from 0 to 3, and I create 6 sub-intervals. What I am doing is I am using the right-hand value in order to calculate each of the heights of the rectangles along the subintervals. Some people up here, once they find the width of the rectangle is 1/2, they will write out their subintervals. Our subintervals here go from 0 to 0.5, and then from 0.5 to 1, 1 to 1.5, and then from 1.5 up to 2, and then from 2 up to 2.5, and then from 2.5 up to 3. Those would be the 6 subintervals that I'm calculating my rectangles on. So for the length of my first rectangle, I used the function value at 0.5 because that was the right-hand value of that subinterval. For the length of my second rectangle, I'd use the function value at 1 as the height. For my third subinterval, I'd use the function value at 1.5. For my fourth interval, I'd use the function value at 2. For my fifth interval, I'd use the function value at 2.5. And for my sixth, I'd use the function value at 3 to determine the height of that rectangle. These can all be calculated. F of 0.5 is just what I get when I plug in 0.5 into this function. So let me go ahead and do that. 3 times 0.5 minus 0.5 squared becomes 1.25. So 1.25 multiplied by 0.5. So 1.25 is the height of that first rectangle because that's the output when you plug in 0.5 into your function. In my second rectangle, I get f of 1. If I plug in 1 into this function, I end up with a height of 2. So we have 2 times 0.5. My third rectangle, f of 1.5. We take 3 times 1.5 minus 1.5 squared, and you'll get 2.25 as your output. That fourth rectangle has height of 2. When you plug in 3 times 2 minus 2 squared, 3 times 2 minus 2 squared should give me a 2, 6 minus 4. And the width is still 5. Again, that's f of 2 is equal to 2. Plus, now we're looking at f of 2.5. 3 times 2.5 minus 2.5 squared becomes a 1.25. So the output is 1.25 multiplied by a half for your width. Again, these are just length times width. And lastly, if you plug in 3 into this function, you get a height of 0. So this last area is going to be 0 times 0.5. I'm going to make this sort of match up with the others. So we have 6 areas, 6 little areas that we're adding up to get an approximation for the signed area that we're trying to approximate. Let's go ahead and add these up. I'm just going to add this up in my calculator. When I added those up, the area of the rectangles added up to 4.375. So the approximate area for the signed area of this function using 6 rectangles is 4.375. So there you go. That's how you can approximate the signed area using rectangles. You may ask, well, what would happen if our curve went below the x-axis? Well, if our curve went below the x-axis, some of these lengths could be negative. In other words, the function value, when you plugged in a number, could be negative, like f of 1.5, if it went under the x-axis, would be a negative number. So you could get negative signed area approximations and positive signed area approximations. Both would work out. I want to point out that we split our interval that we were given into 6 rectangles. And we determine the height of those rectangles by using a function value on some interval on the rectangle. So we had these subintervals, and we kept using the right-hand value of the rectangle to make things work. That was a very specific choice. I want you to realize that we could have made other choices. Specifically, what we did is we used what's called the right-hand rule. When I look at the subinterval, if I use the function value on the right side of the subinterval, then what I've done is use the right-hand rule to calculate the areas of those rectangles. I could have also utilized what's called the left-hand rule. The left-hand rule is where I use the function value on the left side of the rectangle's subinterval. There's another rule called the midpoint rule. You could imagine what this is. I look at each subinterval, and instead of using the right-hand or the left-hand value, I use the midpoint of the subinterval. These are the 3 common ones. Obviously, you could create your own rule if you wanted to, but these are the common ones. Either a right-hand rule, a left-hand rule, or a midpoint rule. And that just tells me which function value we're plugging in. Graphically, we saw that when we used the right-hand rule, we did this. We used 0.5 for our first rectangle, 1 for our second, 1.5 for our third, 2 for our fourth, 2.5 for our fifth one, and then 3 for our last one. If I wanted to use the left-hand rule, I would have used 0 for the first height. Let's go ahead and do that. Let's use the left-hand rule. 0 for the first height. On this purple interval, I would have used a purple rectangle. I would have used 0.5 because that's the left-hand value. On this black rectangle, I would have used 1. On the red rectangle, I would have used 1.5. For this blue rectangle, I would have used 2. And then for this last 6th rectangle, I would have used 2.5 as the height. You can see how that looks different. All right. So we use the left-hand values and we get this rectangle. And then obviously I can use midpoint values as well. Between 0 and 0.5 is 0.25. If I were to use the midpoint value, my rectangle would look like this. My purple rectangle goes from 0.5 to 1. The midpoint of that is 0.75. My black rectangle goes from 1 to 1.5. 1.25 would be the midpoint there. From 1.5 to 2 is 1.75 as the midpoint. From 2 to 2.5, that's 2.25 is the midpoint. From 2.5 to 2.75 is the midpoint. If I were to utilize the midpoint rule, I'd have to add up these 6 rectangles area as an approximation for the area under the curve. Now again, notice this is not going to be a perfect approximation. It's kind of hard to tell, but this isn't a perfect straight line. So we're losing some area here, but gaining some here on this first rectangle. We're losing some area here, but gaining some here on the second rectangle, and so on and so forth. So it's an approximation, but it might not be a perfect representation of the total signed area. So that's the concept of left-hand rule, right-hand rule, midpoint rule.